So good morning. Thank you for joining this early morning on a Wednesday. It's a really sunny day here in Belgium. It looks like I'm dialing in from Brussels, but it's almost the case. The sun is likely shining on the atomium here in Brussels, but I'm dialing in from my hometown. And this is the first of the webinar series that we start with 3if again. After a bit of being away. So thank you very much for joining. My name is Ulrich Saldesaerts. I'm the Managing Director of ELSEC, which is running the 3if activities. 3if is a not-for-profit activity which is supported by the Flemish Government to support the digital transformation for manufacturing companies. And within 3if, we have a series of activities that are related to condition-based maintenance. So today, we'll talk a little bit more about this. For within 3if itself, we have started this activity since about 6 years. And 6 years ago, we saw that there was first starts in industrial IoT and the pickup that was needed to be supported for Industry 4.0. Today, we see luckily that many companies are endorsing this, this idea of digital transformation, especially also in the manufacturing world. And also thanks to some of our efforts, we have been accompanying about 400 companies in Belgium, in Flanders mainly, in taking their first steps into that space. So what we do is we bring some advisory and some techniques and some best practices to those companies on the basis of industrial IoT and specifically data analytics components, and how then to further optimize on the use of analytics technologies and tools. Flanders Industry 4.0 is a project that was started about 3-4 years ago. And within that respect, we do operate today a field lab, specifically on condition-based maintenance. The 3if platform of a field lab is using many different types of tools and technologies, some of the ones that you can see here. And so the field lab is really a case of components that we take into manufacturing companies and showcase what it can really be about. Within 3if, we don't only focus on condition-based maintenance, but for the sake of today and today's topic, we'll be doing that. So why is condition-based maintenance important? We'll be talking about that obviously later on, but for us, it's important because we want to avoid things like this. So this is the Deep Horizon disaster that could have been avoided if probably a much more insights and understanding was received from the platform on the basis of some technologies that existed at the time. And so we are looking to evolve the whole concept of predictive maintenance and maintenance overall on the concept of Industry 4.0 condition-based. So we are using components such as these digital technologies to support digital servitization, to reduce the cost of maintenance and ensure that there's KPIs related to those. So we have many different use cases for this that we can show over the next couple of months and weeks. So maybe I'll hand over shortly the word to my colleague Daniel, who's been working also together with me on Factory Sense, which is using some similar cases, and shortly explaining what we have been doing within Factory Sense. So Daniel, I'm going to hand over the word to you. Good morning to you, by the way.
Yes, hello. Good morning to everybody. Thanks a lot to participating to this webinar series. I will try to show you a bit a part of our project. I will start to share my screen. Hope to work. Okay, I hope that is visible.
Yeah, we can see it.
This is a project started from our field lab activity where we tried and we put together a few producers of IoT devices, connected each one to his own platform, IoT platform, to be able to have an overview of what happens at the factory level. And the target for this project is the small and medium-sized company, not only, but it was the goal to have something available at an affordable cost to be implemented in the real industry. And this factory sense, in the factory sense project, we proposed to provide a sensor kit, 10 sensors, one gateway. The gateway is the connection to the cloud, but 10 sensors can be also an interface connecting the real data from the machines, from existing sensors, and to have a look into the cloud and to see what happens. The business intelligence and system analytics is the second part of the platform, where the data arriving in the platform are used to build dashboards visible by a platform, by a browser into the computer, but also up to the level of a smartphone. We run this project supported from strong partners. We have the project Connected Factories, European Commission, and the Trinity. It's another project we run for the security in the robots. Using the platform, we'll make the connection between the data sent from the sensors, existing sensors, or the new sensors installed from the VersaSense kit, and we'll have an overview into the data in our platform. Different visualization are already available, starting from the raw data, but also from the data we analyze. In the dashboards, we can see the results of the main tool. There is the analyze, where the analyze means that we can see the influence of each parameter. And after the calculation, we can see here we have an influence of 75% and 100% from another one. The small influences probably is not make any sense to consider as useful. So we can rerun the analyze to provide the optimization result. Here, it's a visualization of the results. Between the data, it's much better here. Between the real data collected, in yellow, we have the best situation, the best settings. And if we'll go back to the parameter and we'll modify the input parameter, we'll concentrate our output in the best scenario. And another visualization from these tools. I will spend some time here. It's not related to the condition-based maintenance, but it's visible the variation of some parameters. If here, in place of the tank temperature and concentration in oxygen, we'll have a vibration of a temperature, we can combine in only one visualization. We can combine data from different sensors. And also we can trigger in different conditions. Let's say if we have monitored the temperature of the device, probably of a motor, we have some parameters. We have the motor temperature even in the automation layer. And it's not relevant if my temperature remain at 70 degrees. Let's say it's constant, it's okay. But if the increasing time for this temperature is faster than, let's say, a few seconds, could be an alarm. In this platform, we can monitor and we can put together existing sensors, but also we can put calculated sensors to have a relationship between the data coming from the machine. From another example, we monitor it effectively in a production site. We monitor it from 4 motors, the vibration, and it was visible in this kind of graphic. It was visible that each time a panel was passed there, the motor was started and the vibration was visible. But from the factory side, they didn't confirm like this. They said, no, the motor is completely stopped. So just using the platform and discussing with the person working there was easy to see that vibration came from each panel was flow on the cutting machine. In fact, it was the main source for the wearing of the motors, because a big vibration was induced into the motor, into the bearings, when the motor was stopped. So using the platform, we detected something invisible before. If we will turn this visualization in triggers, we can build effectively a scenario for a condition-based monitoring directly from the platform. I hope that just having this overview will be easy to see the benefit of such using of small tools like this sensor kit, non-intrusive, easy to connect directly to the platform, and building after that dashboards and triggers to monitor a machine. This is the first use case, but up to the complete production. Thank you.
Thank you very much, Daniel, for sharing this. I think that's a great use case in any case. Oops. It's a great use case in any case, and we'll just continue with this use case, and I hope you maybe also will be able to give some further comments, Michele, who's dialing in from Denmark this morning. So Michele, welcome. I hope we are not catching you at a too early stage in the morning. So thanks for joining in. And Michele, we have invited you because you have been co-authoring this great piece of work, really a milestone, I think, in the domain of condition-based maintenance, the Mantis book. And we invited you here specifically to discuss a bit about what this is and how it actually can help the world in condition-based maintenance, the maintenance people out there. And we hope at least also to get a bit of your insights in how we can further improve our own field lab experiences and our own platform. So I'll hand over the word to you. So thanks for joining and thanks for doing this.
Hi, good morning. I'm Michele Albano from Denmark, from Aalborg University, and I've been working some years ago on a project on a condition-based maintenance. The title of the project was the Mantis project, cyberphysical systems based proactive collaborative maintenance. So it had the words proactive and collaborative in that. Now I will. Here's the outline of the presentation. I will talk about the project, then the architecture. Then I will show 4 of the pilots that we developed. And finally, I will provide a few questions that future maintenance platforms should answer. The Mantis project. It was active between 2015 and 2018. And it was an international European project. It was funded by the Excel program, and it had 37 partners, quite a large project, from 12 different countries. Being an Excel project, it had 1 or 2 demonstrators, pilots, per country. So it was quite pilot-centered and very applied, which is I believe, very interesting for you. Objectives of the project. From the point of view of the technology, it had 4 objectives. To innovate on data structures to enable collection of the correct maintenance information. And the idea was able to use the information, for example, to compute root cause analysis, fault prediction, etc. And then we wanted to have also good data structures to process the data both in real time and in batch. Then we wanted also to build a large platform with many possible competing stakeholders that still had to have some collaboration for this business logic. And finally, from more the low level, we wanted to have a system populated with the cyberphysical systems, so a system of systems that could actually apply techniques to allow for condition-based maintenance and proactive maintenance. Now, I will not spend too much time on this slide because you are from the field. Anyway, here we define the 4 kinds of maintenance: the run to failure, the preventive maintenance with periodic maintenance actions, condition-based maintenance, which is based on data readings to decide when to perform maintenance actions, and proactive maintenance, which builds on all the other ones and leverages a lot root cause analysis, etc., to improve maintenance actions themselves. examples of what CBM and also proactive maintenance want to be able to do are answering the questions we have here. Which machines I should take care of in this moment, where are they located, how can I find them, because maybe I don't need the ID of which is hidden inside the machine. I want some way to recognize the machine in a fast manner. When I should do some actions, and also which spare parts do I need or will I need to perform the action, how to perform the maintenance action, and how to do reporting. The technologies that we used in Mantis came from a number of different worlds. First of all, the sensors. We wanted to be able to employ existing sensors of the machines and new sensors that had to be, at least in part, quite cheap, to be able to power our platform. So, in that sense, we wanted the IoT, Internet of Things, and cyberphysical systems to provide the platform, and we also wanted to take care of the 3V of the data: volume, velocity, and variety. Now, Internet of Things. I believe that all of you know what it is. They are embedded systems that are always connected to the internet. So they are able always, or close to always, to exchange data with some place where data is processed. Cyberphysical systems inside is another term that says that this embedded system can have an impact on reality. So it's a bridge between the cyber world and the physical world. Then the cloud is another component of our platform, because we want to be able to deploy applications in an easy manner. We want to have elasticity, so we want to be able to scale the power of our computational platform when needed. And also, if you have everything on the cloud, it's easier to maintain the application themselves, in general, to manage them. And here, another technology to be considered, actually an ISO standard. This standard defines how and where in our system of systems to perform some kind of data processing. For example, on the bottom, we have in the machine data acquisition, then we have manipulation, etc., up to advisory generation. And we applied this vision to our system to be able to find if we were not covering some of the pipeline that we needed to cover to be able to do proactive maintenance and CBM. Now, the Mantis platform. The idea was to develop a framework for proactive maintenance. Actually, it was mainly CBM. Some of the pilots were able to do some kind of root cause analysis, but it was not that easy. And we will get back to the motivation in a few slides. So we had a mix of 4 main technology families. One in the factory, so real-time sensor data acquisition. Then we wanted to have a middleware that was fast and high-performant to connect the factory to the cloud. Then on the cloud, we wanted to be able to do data analysis and support decision-making. And by the way, we wanted also to be able to do some preliminary data analysis in the factory. And finally, we wanted HMI, a human-machine interface, because having just the data is not enough for an engineer to understand what's happening. We want to be able to show the data and the output of the data analysis in a smart manner. Here you can see the 3 tiers of our architecture. One on the edge, so in the factory. Then we had a platform tier on the cloud, where we had other business logic was implemented. And finally, an enterprise tier. which is mainly close to the customer. Let's get through them one at a time. The edge tier uses edge computing, so computing in a mini cloud, let's say, close to where data is collected, to collect data from the machines, pre-process them, and filter them, convert between data formats, and in general, cache them, and finally send them to the platform tier. By the way, we also wanted to do CBM in here. So we want to be able to have a very limited data analytics already in the factory, some kind of preliminary visualization of the collected data. In general, we want to support the engineers and the technicians that were in the factory. They will not be able to have a very powerful data analysis, but still sometimes being able to visualize, for example, temperature, humidity at the same time is already enough to help them. Obviously, CPS were very involved in this tier. Now, platform tier. Here we have a computational platform that is able both to transport data in a very fast manner, store all the data, and here we adhered to the MIMOSA standard. So we wanted to be able to collect the data on the machines and on what's happening in a standard manner for interoperation with other partners, for example, and other systems. And we also want to be able to have some kind of distributed file systems for redundancy, for scalability. And here we want to be able to process data online as batch and as stream. Here we had the three main and powerful ways that data could be processed in this kind of systems. First of all, we want to be able to compute the remaining useful life of the components. We want to be able to do fault prediction, so to forecast when a problem was going to happen. We also wanted root cause analysis. So from the data about the weird behavioral systems, from the outliers, we want to be able to predict what was causing the problem. And these three things are PM, proactive maintenance, not just CBM. So it was the grand vision of the Mantis. And finally, the enterprise tier. Here we are talking about visualization of the data to the customer after they are decorated with more information computed by the platform tier. And we also wanted to provide an interface for the customer, for the engineer that is managing maybe tens of factories, to be able to send comments to the platform edge tiers. You can see here two examples of interfaces. One, the one on the top right, is a dashboard that probably you've seen so many times. The other one, the one on the bottom left, is a screenshot of a virtual reality interface. Now, the complete architecture had to expand on the tiers of the project. We had a component of the architecture on the machine. Then we had the local middleware in the factory. We had the edge local, which is a set of computers still in the factory, but they are like a mini cloud for the preprocessing of the data. Then we had a real internet middleware. And then we had data analysis and human-machine interfaces. On the machine, we had PLCs, CNC. We had all those kind of elements integrated in this component. So the idea was to integrate what the CNC could tell us regarding what's happening, to integrate the sensors that are talking already to to the PLCs with the new sensors to collect all the data that can be useful for the maintenance of the machine. The local middleware had to be fast enough and reliable enough, but not too much. The idea was to have something that was not so computationally expensive, that can be executed in not so powerful computers, but that was still able to interact with the protocols of the machines. For example, OPC-UA, if the machine allows for OPC-UA, maybe Bluetooth to be able to connect to the new sensors of the machine, etc. Now, edge local. Here we have, let's say, mini cloud, a small number of computers, maybe just one computer, to do the preprocessing and pre-visualization of the data. This edge local had both to provide those capabilities to the user, to the local user in the factory, and also it had to be the only elements that is contacting the internet. So we wanted to protect everything inside the factory and have just one computer or one set of computers that could that had to be protected from the usual problems you can see from the internet, cyber attacks, etc. And it had also to perform some kind of a caching of the data, processing, and then to contact the real communication middleware. Now, the cloud middleware. Here we want to have a very high performance middleware that was able to be a bridge between the factory and the cloud. This middleware had to extend all over also the cloud to be the platform where all the computation had to be performed, and also that was going to feed the information to be visualized to the HMI component. This analysis was a component powered by the cloud, where we were performing all the prediction models, the comparison between the data and the normal behavior of the machines to find outliers, and where we were distilling the data into information to be shown to the user. And here also we had the IMDSS, the Intelligent Maintenance Decision Support System, where we were building a knowledge base of the normal behavior of the machines to be able to find outliers, for example. Now, why PM was complicated? How can you do root cause analysis and find out the problem of this fault if your platform is not going to see many faults? In fact, errors in machines are extremely rare. Sometimes you have one fault every 150 days, sometimes even every 500 days. So we were able to do some analysis of the normal behavior of the machines, but we didn't have many errors and many faults to train what we were building. Still, we were able to provide a knowledge base of normal behavior to find outliers. As you can see, we had to move from proactive maintenance to condition-based maintenance, because it was not so easy, for example, to compute the remaining useful lifetime if I don't see the end of lifetimes to train my systems. And finally, the HMI, the last component. Here we want to be able, as we said, to provide the data, to show it in a smart manner, because maybe you have 10 gigabytes of data and you want to show just one graph to the user. We had to let the user identify the interesting information. For example, highlighting the graph when we are having outliers. And so it was also an important component of the Mantis. And now the pilots. I will talk briefly about 4 pilots. The first one was in Portugal. We had a sheet metal bender produced by the Adira company. And you can see here in the red circles 2 sensors that we added to the machine, 2 accelerometers, to find out vibrations and the speed of the blade to understand if they were being outliers. We also added a sensor to the oil of the machine to find if the oil was getting worse, and we're collecting all the existing data from all the existing sensors of the machine. So the ones that were already inside the machine before we started the project. So we said, this machine is press brake. So it had a blade, sorry, it was getting on the metal sheet and it was deforming it with a very high precision. For this motivation, the behavior of the machine was very precise. And that's why we were able to do something with the accelerometer, because the machine was going to perform the deformation of the metal sheet exactly the same manner always. It was started to be a little different with outliers. So some data, some information to play with. Here you can see the implementation. We had on the edge here a lot of data that were collected, both from the existing machine sensors, from the accelerometers, and from the new oil sensor. We had some kind of processing of the data locally, mainly compressing of the data to be sent through a AMQP middleware to the cloud, and then we had some machine learning just to find outliers. And then we had a dashboard. And here you can see the full deployment view, what was happening, something on the factory, something on the cloud, and the HMI access, which was on a browser. So on the cloud, we had a web browser, a web server, and your enterprise tier was going to be in your house or in your company, in your office, since you had the browser to get data from the web server in the cloud. And finally, you can see the human-machine interface. It's a normal dashboard. Okay, one more pilot, a press machine. This time, it's something huge. You can see the size from the picture. Here, we are scaling up around 1,000 times regarding the force of the machine, and it was a press machine. So it was going to stamp with very strong heats some material. Here, we decided to build new sensors, not use existing sensor machine, not only that, not only using normal sensors such as accelerometers, but actually build something to integrate in the components of the machine. Here you can see the visual of the machine itself, and all the CPS, cyberphysical systems we integrated in different parts of the machine. And here you can see the implementation. It's not so different from the other ones, obviously, but you can see here that different technologies were used. Here, in this case, we have Apache Kafka and other techniques to do big data processing, while in the other case, we didn't have big data. We had just machine learning. Here we have machine learning, big data, and all other techniques for real-time batch processing of all the data that are being collected. Now, one more pilot, also in Spain, pultrusion. It's a way to take fibers, for example, glass fibers, carbon natural fibers, impregnate them with resin to be able to create a very strong material with very good chemical resistance and electrical and thermal insulation. Because material, for example, is used for the waterproofing of the Harris tunnel in Asturias. As you can see here, we are not talking now about machine, but about a shop floor. So a long machine that must be perfect in terms of temperature, etc. Because in pultrusion, if the resin that you are using to impregnate the fiber is too hot, you will burn the fiber. If it's too cold, the process will not be complete. Here we had to collect data about all the shop floor, temperature, humidity, air extraction capacity, and from the machine itself. So internal temperature, oil tank pressure, etc. And here you can see the implementation. As you can see, we have this time in the factory a lot of different parallel data streams from the machine, from different parts of the machine, which is quite long and composed by different stages. And from all the shop floor, you can see here a number of technologies that are used on the machine. And in the end, we're providing a dashboard that had to find out in a very fast manner, using different colors, what had to be shown to the user. And finally, the last pilot. Here we have medical devices. So we are talking about much smaller and cheaper machines that must be kept in perfect condition, because this time, every time there is a problem, a patient either will not be diagnosed or it will die. By the way, there is the problem that we had to find an issue in advance, because it was not possible for the hospitals buying those machines to do redundancy. It was too expensive for them to buy multiple machines. And it was also impossible to move the patient to another hospital having that machine if the machine broke down. So we had to be able to find in advance what was going to happen while keeping the monitoring platform cheap enough. And here you can see this system, this e-alert controller, which was connected with the machine, which was getting data from the sensor of the machine, and which was going to preprocess the data and allow for the visualization. Here you can see in particular quite a detailed list of what the small device was doing. Filtering the data, putting them in a format that is comparable with other machines of different families, but with different functions, etc. And finally, here you see the e-alert controller software. As you can see, now we're talking about something more mundane. We are sending SMS to the users, we are sending emails. So this time we don't have an extremely large machine to monitor, but we have something different to do. And now a comparison of the use cases. We had a sheet metal bender with a traditional machine, quite large, but not huge, that had to be monitored with cheap new sensors and existing sensors. We had a press machine, which is so huge that we could invest more in other sensors. We had a pultrusion machine where we had to sensorize all the shop floor, and we had a life-critical but cheaper device, a medical device, that was going to be sold in a huge, not huge, okay, in a larger volume, because if we have sold 50 sheet metal benders, 10 press machine, and 10 pultrusion machine, the medical device probably will be hundreds or maybe thousands. And here, finally, the last slide, the questions about the future of maintenance. For example, do we want to have a lot of human intervention in the maintenance process, or do you want to do that as much as possible on the cloud and with cyber techniques? Is it possible to have real time, or we just want to have visualization in the factory real time and everything else must be batch? So it's possible computationally to produce something interesting in real time or not? What is the granularity we want to provide to the data visualization in space and time? Do we want to have the customer in the loop, or we want to have different companies performing maintenance? Do we want to use advanced communication techniques, blockchains, or something else, or in the case of maintenance is useless? Okay, for asset management, it's useful, the blockchain. But for this kind of data collection and processing, is it useful or not? We don't know. We want to have insourcing or outsourcing. Who is going to do the maintenance? The company producing the machine, or some other external third-party company? We want to have explicit modeling or data-driven techniques. So we want to have a lot of domain knowledge in the data processing, or just want to do big data and machine learning without so much modeling of the data? And finally, do you want a lot of robotics for maintenance, or is it not interesting for the future? And here you can see the advertisement for our book. It's open access, it's free, and it's edited by myself, who is the sensor expert in the group and the middleware expert in the group, Erkki Antunen, who was the mechanical engineer, Gregor Papa, the expert in artificial intelligence and visualization, and Ulko Zurutuza, who was going to be the glue between all of us. Okay, I will provide the slides for you to download if you want. Thank you for your attention. I'm open to your questions.
Hey, Michele, thank you very much for this very interesting overview. I think you raised, in any case, to my world, quite a number of questions and ideas. Specifically, if you can go back maybe one slide, the slide where you put indeed the future of maintenance strategy. But before I go into this one, I think for us, and probably also for the participants, I think the biggest question is, what type of challenges have you seen in the different use cases? Because one challenge that we are constantly facing is the challenge of the normalization of the data. So you can have multiple different devices, both from the sensing as well as from the IoT when you're using cyberphysical, as well as in terms of the data analytics. There's many different models that we can apply. So first question is what was your experience there? And did you try to do something from within Mantis towards this? Are you saying, okay, let's basically use the internet protocol as a basis? Some people are advising to go into OPC, which we don't. Some other people are very agnostic to this, and they can use anything that's out there. Like sometimes we use from Modbus to the latest edge technologies. But I think that's really one of the biggest questions that we see today in terms of doing this. I mean, from a hypothetical perspective and from a theoretical perspective, this does make sense. But on a practical terms, it's much more of an issue.
Okay, so you're talking about data and normalization. I thought you were talking about semantics of in ontologies for the data. Actually, we're talking about the protocols. In our case, the idea was to have a plethora of protocols between the edge local machine and the machines, and then have just one kind of protocol after that. So the idea was that the edge local component was going to be the glue and the very agnostic element that was going to accept any kind of data. So here we said, customers, pilots, you can have everything you want in your factory, obviously, because we must work with what we have. But after the factory, when you get out of your factory and you get to the cloud, you want to have some kind of very similar protocol for all the pilots. So we had on one side SCADA, ERP, OPC-UA, Modbus, Bluetooth Low Energy, ZigBee, and or even cabled protocols. And we collected everything on the local edge. And after that, so the local middleware accepted everything because we had to use what we had. But after that, from the local edge to the outside, we had high performance messaging buses, mainly AMQP or something very similar, and usually RabbitMQ at the time. Now they prefer different kinds of messaging middleware, but at the time it was RabbitMQ.
And did you, in this case, had to transform all of the data gathered into RabbitMQ or AMQP, or did you use basically the two message bus systems as just a carrier for the data that you captured?
Okay, in the beginning, they were just carriers.
Okay.
In the beginning, in one case in particular, we were transferring Microsoft SQL log files, so the databases, through the messaging bus up to the cloud. That was, let's say, an horror story, really very low level.
Right?
But, yeah, that's terrible. But after that, we decided to have some kind of JSON like formats for the data, where we had metadata to describe what was going to happen, and then JSON data over AMQP. So we had this kind of steps in that pilot. Every pilot was free to do whatever they wanted, but I know that all of them did some kind of pre-processing of the data, because we wanted to be able to apply technique to different families of similar machines. Maybe we didn't want to mix the knowledge of Philips and of Adira. Still, Adira had different families of machines. So they wanted to have a uniformization of the data. So they had some kind of transformation. All of us did that from the edge local out.
Yeah, I guess that's. I think that's a sort of the common pain that that we definitely also see, and that we probably all experience out there in the field. In that respect, is there something? Oops, is there? Oh, shoot! I think I might have lost the screen here. And see if Michele is still on board there. I'm
still here, yes.
Okay, yeah. Okay. I didn't see you for a second because I lost one of my screens here. So sorry for that. So is that something that you have in the Mantis book as one of the recommendations in terms of this? So you're saying here storing all data using MIMOSA-like design. And is that then the way you think that we should be going forward on this domain? So should we try to get some form of normalization happening up front there?
Yes, yeah. It's quite important, because if you want to be able to use the data in the future, you should have some kind of foundation for how you manage and transform it.
Yeah.
Okay. So yeah, the idea is I will not say MIMOSA as the only good standard. Anyway, in Mantis we like that a lot. Maybe you will use a different kind of standard, but still doing some kind of mapping between the raw data and good ontologies that you define maybe is very important. And if you adhere to a standard, you are leveraging existing knowledge, because if MIMOSA like that, people plan it in a smart manner. They have motivation for having structures such as MIMOSA.
So returning to the question, what did you see as the biggest challenges that you had to encounter within the different integrations and the different use cases?
Well, to reach PM, productive maintenance, the problem that we didn't have enough faults, enough errors. So it was not possible to get to that level. That was really, no, it was impossible to reach that level. Then I think that Urko, also our coordinator is online, he can provide more information regarding maybe other big problems. Are you here, Urko?
We know that Urko had a bit of a challenge with the babies.
Yes,
good morning, Urko.
Hi, good morning. Babies are more challenging than machines many times, right?
Yeah. Condition-based maintenance for babies, that doesn't work.
You can never predict. So, so the challenging situations are a lot, right? As you said, well, in Mantis, we try to cover both greenfield scenarios, so companies that start from scratch, but they have at least some minimum technological space, right? And then we had also quite a lot of brownfield scenarios. But I think that a lot of challenge came from the data analytics part also. So as Michele commented in his presentation, I think quite well, you never know when will you have a faulty scenario. So we were relying a lot on techniques such as root cause analysis, or trying to estimate the remaining useful life of one component of the machine, right? So if you start from a machine that is new and the machine has a useful life of 15 years, and you will not have any fault in, let's say, 2-3 years, then it's really challenging to know when will it fail, right? Because you don't have any experience before, and that's really challenging. And that was one of the biggest probably issues on one project that runs for 3 years. And also when you run like 1 year and something for putting sensors into the machines, and then you start monitoring and you don't get any fault, right? But of course, it is challenging, because in a short time you don't have any information about failures. So you cannot monitor, so you cannot train your models, so you cannot get both root cause or remaining useful life. But of course, algorithms are already there. They are learning every day, and hopefully or maybe not, right? So the machine vendor doesn't want to have any failure actually, but maybe at some point it will start learning from machines. So there are some of the use cases that also rely on not one machine, but in a series of machines, in a lot of machines that you have spread in your customers all around the world. And that was also quite a good example where, because you can learn from one machine and put the learning stuff into the other one. So that was also good, but it's also challenging.
Right, thanks. Yeah, I think another challenge that we are facing in many occasions is some consideration and concern from manufacturing companies in taking some of their data to the cloud. You also see it as a sort of a given, a baseline. So with cyberphysical, with the concept of edge, you immediately also consider going to cloud. Was this a challenge for you, and how did you cope with it?
So yes, it was challenging also, that one. So well, it depends in which type of use cases. We saw some of the use cases making their own cloud on their premises. So okay, but some other ones using services from others, like Azure, for example, right? I think they managed to have I think some of the cloud providers, you can choose where your data will be. I mean, in which country, or maybe at Europe level, right? So you don't have big issues in that sense, because you are not sending the information to maybe United States, so on. But it was challenging. Another one that is challenging is one, and this was really, it's a stopping thing when you have your machine in your customer, and you can maybe not monitor the machine because maybe the customer is not, because the customer doesn't want you to monitor the machine, because maybe the customer is, outperforming with your machine, putting it on a stress situations, which means that maybe they are breaking the warranty, but they don't want you to monitor how do they use their machine right now, because they maybe are out of the warranty.
So Michele, if you can take it back to the one before last slide, that was the other thing that I wanted to quickly talk about. So yeah, that one. So you put there is real-time feasible, and then the last point, the service robotics for maintenance. Yeah, I think there probably you answer a bit of the question, because we do see quite a lot of robots being put into place for maintenance, and of course many of those robots need a real-time interaction. So I think to some extent some of the questions that you put here are already being answered by the real life cases. But,
in part.
Yeah, okay, go ahead.
Because in my opinion, real time here is not the control of the robot. Yeah, you have to control robot in real time, fine. Here we are more talking about performing not CBM but PM in real time, computing root cause analysis, remaining useful lifetime in real time. Here the question is, okay, the data is collected in real time, is shown in real time, but the decoration of the data. Here's the temperature, it will break in 15 days. Is it computable in real time or rolling batch? That's the meaning of this question. And yeah, after that, the robot must be controlled in real time. It's totally normal. But this part, the computing of the proactive maintenance information, that is still, in my opinion, an open question.
Okay, I'd like to add a question to this list, and that is the one whereby how do you integrate, in this case, third parties in the field? And with third parties, I mean, could be second parties, but in any case, those companies which are not directly involved with the manufacturing or with whatever the company does in this case. So meaning, for instance, could that be a supplier, provider, a vendor, who has it, for instance, in a maintenance contract that he needs to perform his activities on the machine. And so then the question is, how do you relate back to those organizations? Sometimes a company is renting a machine or has a machine in service as in a service model, and then so the service provisioning has to come from the provider, but the provider doesn't have to give access to the data or to the insights of the dashboard even to the customer. So then that piece of problem pops up. So I think in many of those cyber physical environments, we do see the challenge in how do we relate with others? How do we can also, for instance, do an analysis on maybe benchmarking? Is my machine that I bought from supplier X operating in the same way as company Z and K? Is my machine performing in a similar way? And so how can we measure this, and how am I assured that it's going to actually be something useful? That's is something that you guys have been thinking on that level. So how to integrate, we know, for instance, there, and we participate in an activity called international data spaces, where there is a bit of interaction on that domain being discussed. And so where some of the data collected from the factories can be reutilized for other purposes. Is that something that you guys have considered as well?
Partially. Let's say that here we have the question about the customer in the loop. So you want him to be part of the loop of the information, or you want to provide him only already cooked up information. And then we have insourcing versus outsourcing. You want the company building the machine to perform the maintenance, or you want a completely third party. Back at this level, you are talking about an ecosystem of companies, all of them interacting. That was not covered by Mantis. Will they consider the automatic interaction with the asset management companies, etc.? We just kept at the level of considering a potential maintenance company, the producer of the machine, and the user of the machine. Those parties mainly. Not everything else that we must consider. So we didn't ask ourselves how much information should we tell to the supply parts provider. We didn't ask that question. Urko? Okay, I think that the answer is one. Yes.
Okay. All right. Good.
Yeah.
In any case, well, guys, it's 10 a.m. Already past. So I would like to thank both of you for your early attendance and sharing your experiences here with us this morning. Let's be connected in any case on the future development of what you have been doing, and definitely, hopefully, we can include you somehow in some of our ongoing activities. I think there's a lot of components that we definitely can join efforts in, and also likely with some of our attendees. So I'm very much looking forward to continuing that discussion. So thanks a lot to both of you. Let me quickly take over the screen and end this first of our new series of webinars from 3if by a couple of ideas. So we are participating in one of the digital innovation hubs called Trinity, which is on robotics, not really specifically maintenance robots, but those are included as well. We just recently closed an open call, but by the end of the year, we'll be doing another open call. And so we invite you all to participate there with some interesting use cases. And I think maintenance use cases, condition-based maintenance use cases, where you use cyberphysical and, for instance, robotics are definitely welcome here. So beyond this, I'd say another one for us to consider is the fact that 3if is also participating in connected factories too already, where we are looking towards the pathways of factories and how they need to progress towards factories of the future. So the future factories moving on towards Industry 4.0 and what that really contains. And there we do see everything in relation to cyberphysical as the very fundamental integrated component. And whether it's Industry 4.0 or it's edge computing combination with industrial IoT, this is the way forward, and this is definitely the way that we see that the future needs to happen. So condition-based maintenance is definitely a major part of this. And then what I can also exchange with you are a couple of thoughts. So every Tuesday at noon, we organize our industrial cybersecurity events. Yesterday we had one, and the webinar has been recorded and has been put online. So we had a session with Microsoft, but we've had a couple of other sessions. Next one will be on ransomware. So I definitely invite you to come and take back a look into how security should be applied into industrial cases, and where we can see that there's an opportunity for integrating security both on the edge, in the middle, and towards the end, and getting an end-to-end security perspective. But when we consider things like integrating JSON, integrating over REST, and also over MQ, we also need to take into consideration how to connect to identity and access management. And so I welcome you to also consider the different identity and access management activities that we run. And then finally, when we talk about the future, 5G is definitely important. And so Next session will be next week. So this is still talking about the session that we had last week. But next week it's also with Koen, where we'll be detailing some of the 5G use cases for industry and actually also for maintenance being utilized already in Asia Pacific. And so I think that there's definitely a lot of things to learn on how we can continue using cyberphysical in that respect. So with this, I'd say thank you all for joining here from Brussels. And I can do like this and make sure that the atomium is fully covered. Then you don't have to see my library, which is actually really behind me. And I'd say thank you again, Michele, and yeah, Michele, you're showing your pieces of art.
Exactly. Yes.
Great. So you brought some Spanish art to Denmark. Portuguese. Okay. Yeah. All right. Well, thanks a lot, Michele, for joining in, and you as well, Urko. Good luck with the family and with the kids, and I hope to be able to see you again face to face, maybe towards the end of this year, in a safe and correct environment. And in the meantime, I would say safe to all of you, and I'm looking forward to seeing you again, definitely already next week when we have another one of these series. Again with Microsoft in this case on their view on using industrial technologies within the Microsoft platforms. So thank you very much for joining, and hope to see you again soon.
Bye.
Thank you. Bye bye.